So today we will be looking at the flow through porous media, especially the flow of water through the earth, which can also be referred to as groundwater. So there have been countless measurements that have confirmed that groundwater indeed flows and in some cases can move at great distances under the ground. In unsaturated zones, that's the region between the ground surface and the water table. Water percolates straight down. It's kind of like water passing through a drip coffee maker. The water in these zones move due to the downward pull of gravity. The differences in pressure can also cause the water to respond differently. Pressure can cause the groundwater to flow sideways or even upwards. Now, there's a lot we can go into to explain why water moves this way in the ground. However, that will take longer than 4 minutes. We will just focus on how the water moves through the ground. The rate at which groundwater flows at a given location depends on the permeability of the material containing the groundwater. The groundwater flows faster in more permeable material than it does in less permeable material. This can be observed in this graphic below. So as you can see in this one, the material is more permeable, meaning the water drips at a faster rate. This one has less permeability than the one before, so it drips at a slower rate. And then this one is the most permeable out of the three and has the least amount of flow. This rate would also depend on the hydraulic gradient. The hydraulic gradient is the change in a hydraulic head per unit of distance between two locations as measured by the flow path. We can see the equation right here. This is the difference in head, and that can be observed in this infographic above. So this would be H1, and this is H2. And then J is the distance between the 2 points along the flow path. So this arrow represents the flow path. So this distance J is this value. Hydraulic gradient is calculated by dividing the difference in a hydraulic head between 2 points by the distance between 2 points as measured along the flow path, as we can see again in the equation. A hydraulic gradient exists anywhere the water table has a slope. Typically, the slope of the water table is so small that the path length is almost the same as the horizontal distance. We also get into Darcy's law. Darcy's law can be modified to represent the velocity of flow by a quantity called discharge, which represents the volume of water passing through an imaginary vertical plane perpendicular to the groundwater's flow path in a given time. Discharge depends on the hydraulic head, the area of the imaginary plane through which the groundwater is passing, and the hydraulic conductivity, or K. K represents the ease with which a fluid can flow through a material. It depends on factors such as viscosity and density of the fluid, but mostly the permeability of the material. Here is Darcy's law right here that represents this equation. This equation states that as hydraulic gradient increases, discharge increases. Also, as conductivity increases, discharge also increases. In simpler terms, the flow rate of the groundwater increases as the permeability increases, and as the slope of the water gets steeper. Here are all my references, and I hope you enjoyed this as much as I did.